I know that the whole picture is in the slides and the name, it is really intimidating. Okay? The acronym is pretty easy though. It's Malditov mass spectrometry. And you may wonder why we even talk about such complicated methods, but this is a top-notch method of molecular diagnostics of microbial diseases. Okay, and I'm gonna fairly slowly go through each letter of the acronym to make sense out of it. Okay, so we're gonna start with the letter M, which stands for matrix. Okay, so you have some kind of a matrix. It's a chemical, basically. It really is a polymer. Okay. To which you add your sample. In this case, we're going to step away from coronavirus infection, just bacterial sample. It's a bunch of bacteria, okay? So you add your sample. And you mix them together. So M stands for matrix, A stands for assisted. So matrix in this case serves as a helper. So matrix assisted. Okay? Now what is LDI? L stands for laser, D and I stand for desorption and ionization. What we're going to do here, we're going to take a laser and blast, just like in the Star Wars movie, we're going to blast a laser onto the mix of the matrix and the sample. And just like in the Star Wars movie, this mixture of matrix and the sample is going to quote-unquote explode, okay? And we come to two more words. Desorption and ionization. So especially your sample, what's going to happen to it? It's going to be blown in pieces. We clear? And you will have a whole bunch of different pieces of different size. Do you see the size? Now, since laser not only blow it up in pieces, but will also ionize them, these pieces will have charges. Does that make sense? Is that understood? Like different positive charges. Maybe plus 2, I don't know. Okay, plus, whatever charges are. They're all going to be charged. So far, we deciphered multi. Matrix assisted, laser, desorption ionization process. Now what you do next with these particles with different size and charge? They enter a tube with electromagnetic field surrounding it. I'm going to make one statement just so everybody agrees. So when charged particles enter the electromagnetic field, they start flying. Does that make sense? Because, electromagnetic field kind of pulls them. Are we clear? Two questions. First, since I told you that electromagnetic field makes charged particles fly, which particles will fly faster? With a smaller charge or with a bigger charge? Bigger charge, yeah. The bigger the charge, the faster they will fly. Does that make sense? The less time they will fly. TOF stands for time of flight. Hold on a second. What about mass? Which ones will fly faster, small or large? Small. So at the end of the day, and these particles are going to be flying through the tube, okay? The time of flight will be proportional to the mass. So the bigger the particle, the slower it flies, the longer it flies, okay? And inversely proportional to the charge. The bigger the charge, the smaller the time of flight, the faster it will go. Are we good so far? Clear? Okay. So you have a detector at the end, whatever it is, I don't know. And what this detector is capable of doing, it's going to detect all those particles. Does that make sense? And you're going to see at the screen of the computer monitor a graph that looks like this. Well, more or less so, where each peak corresponds to a particular particle. So that's on the y-axis it's intensity, and on the x-axis it's mass to charge ratio. Does that make sense so far? I'm going to wrap up the whole method. I'm going to go over it one more time. So now look, basically at the end of that tube you manage to separate the particles that have been produced here based on the mass to charge ratio. Are you with me? We good? So let me go over this whole story one more time and then we'll get to the application. So you mix your sample with a matrix, blast it with laser, which will desorb your sample, blow it in pieces, and charge those samples. These charged particles enter the tube because of the electromagnetic field, fly through the tube. Okay, the smaller ones fly faster, the ones with the bigger charge fly faster, and they are detected, and the graph shows you the separation of the particles based on the mass to charge ratio. What's so exciting about this method? Turns out that if this is your, I don't know, E. coli, every time you load E. coli into your machine, the graph at the end will be the same. Does that make sense? So now you can do the reverse process. You accumulate an enormous database which contains mass spec signatures of many individual bacteria. Does that make sense? Then you have a patient with unknown infection. A little bit of an obstacle, you need to have it in the pure culture. Once you have the pure culture, you get the sample of your culture, load it here. From what I know now, it's 20 minutes. In 20 minutes, you don't even need to look at the graph. The machine will compare the graph that you got from your sample and the graphs that it has in the database. And if it finds the matching, basically like, fingerprints. If it finds the matching graph, boom, you've got the answer. So you get around the most important problem that you find only what you're looking for. Now you really, you find whatever it is. That makes sense? It is really a forefront of molecular diagnostic, microbial diagnostics, shitload expensive, like $750,000 for the machine. But processivity is great, diagnostic capability is phenomenal. Okay, questions here? Okay, let's move on to